All right, so let's begin. We are in section 5.3, and 5.3 talks about the fundamental theorem of calculus. And there are, in fact, not one, but two different parts to that theorem. And so let's talk a little bit about what we know so far, what we're going to talk about today before we dive into the content. Ooh. All right, so what do we know? We've talked about approximating area with rectangles. That was something that we covered a couple classes ago, and then we had one more question like it on the quiz this past weekend. So knowing that sometimes we can divide shapes up into shapes that we know, rectangles, to go ahead and help us find the area, knowing that it might not be exact, but it might be pretty close, okay? We've also talked about finding exact area. And so thinking about if we happen to know that the shape of a curve is a trapezoid or a triangle or a semicircle, then we can use formulas that we already know to find that exact area. Now, some folks have asked a really good question, which is what happens when that shape that we're trying to find the area of is not a nice geometric shape? And so that's really where I want to connect that idea of exact area. Okay, so when we find exact area, sometimes we can find it with geometry, all right? And if we can't use geometry, then we go ahead and use definite integrals, okay? So we'll use definite integrals to help us find exact area when we don't have a geometric formula. And so if we think about the difference between a definite and an indefinite integral, I'm wondering if someone can maybe summarize the difference between those two for me in the chat. What is the difference between a definite and indefinite integral? Okay, definite has an interval of x values, exactly. And so the symbols look so similar, right? We've got our integral, we have a function, we have the dx, all right? So that's one of them. And then we have a different function, dx. And the only difference is that a definite integral has bounds. We usually say the lower one is a and the upper one is b, and the indefinite integral does not have bounds, okay? So one thing I've noticed is that sometimes on questions where it's just words describing what you're supposed to use, sometimes students have difficulty knowing what to do, but it turns out that it's just a vocabulary issue. So that's really why I want to clarify the difference between definite and indefinite integrals, okay? All right, so what's new? Well, what we're going to talk about a little bit today is the average value theorem for integrals. So we didn't quite get to that at the end of class on last Wednesday, but we're going to talk about this average value theorem. But we really want to notice that it's going to be the average value theorem for integrals. And sometimes instead of saying average value, folks might say mean value, but it's for integrals, which means that it's different than the mean value theorem we learned in the last chapter. Okay. But the focus of today's conversation, and really the theme for this week, is how do derivatives connect to integrals? And how do we evaluate definite integrals? So we've talked about this a little bit before, evaluating the definite integrals, but it's definitely something that we really want this to be a very fluid practice for us, okay? So we want to practice this a lot. think the biggest challenge conceptually today is going to be in around the second point, which is how do derivatives connect to integrals? So that will require a lot of sort of brain power. And then the evaluating integrals, I think, will be a little bit more procedural. Okay. And so if we return to the regular size of the screen, that's what we know and that's what's new. Okay. Before we begin, are there any questions? Okay, I've got a few thumbs up. Seems like things are going well. All right, so let's move along. So the average value theorem for integrals, okay? What we're gonna do is we're gonna start off with some pictures, we're gonna draw some things, and then we are going to go take a look at the actual theorem and think about how that applies to what we just found. And so let's take a look at this first example right here, okay? So in this first example, it says region 1 is the triangle, okay? And so our first task is to go ahead and find the area of region 1. And in particular, what that means is we want to find the area of this triangle right here. All right. So how do we find the area of that triangle? Not a trick question. Yeah, 1/2 base times height. 1/2 base times height, perfect. All right, so in this case, can someone tell me what the base is and what the height is for this particular triangle? So what values might we want to plug in? Base is 2, height is 5. Look at that teamwork, I love it. All right, base is 2, height is 5. Let's do a little reducing before we actually multiply things out and we get an area of 5, okay? So that means that the yellow triangle there, it has an area of 5, right? Okay, so now let's look at this part B. Part B says draw a rectangle that has the same length along the x-axis as region 1 and has the same area as region 1. What is the height of that rectangle? All right, so if we take a look at this triangle, but now I'm saying I want you to draw a rectangle that has the same length along the x-axis as region 1, as the triangle, and has the same height, the same area as that region. What might that rectangle look like? So take a moment if you feel so inclined, maybe go ahead and try and draw a rectangle right on the screen here. What does that rectangle look like? I agree, rectangle is base times height, but I'm also giving you some specific information. All right, so what might that look like? Not of the triangle, of the rectangle. Ah, okay, okay. I see some drawings. I see some guesses. Okay. So let's see. The rectangle on the screen right now looks to have this as the base, right? And it looks like it goes up to 2.5. So like here-ish. Nope. I would say more like here, right? And then if I finish the other sides of the rectangle, I get something kind of like this. And the claim here is that this rectangle that has a base of 2 and a height of 5/2 has the same area as that yellow triangle. Okay. So let's maybe capture what some folks are contributing in the chat. So it says draw a rectangle of the same length and has that. What is the height of the rectangle? So we know that the area of a rectangle equals base times height. All right. And so we want the area to be 5. We know the base is 2, and we want to know the height of the rectangle. And if we do a little bit of algebra, we get h equals 5/2. Perfect. Okay, so 5/2 is 2.5. And if you go back up to that purple rectangle, it should have a height of 5/2. Okay. All right. So this last piece, I think, is the trickier one. Using calculus notation and algebraic notation, write a mathematical expression that represents the equality of your answers from part A and part B. So if I wanted to write part A using calculus notation, what might that look like? Like, what kind of notations would help us out here? The integral, very nice. Ah, okay. So we don't know what this function is, but we can say generically that any function, we can say f of x or g of x, whatever sort of suits our fancy. And so, yeah, I think that we could say that the area of region 1, we could say, is the integral from 0 to 2 of f of x dx. Okay, so this right here our part A is represented by this. Okay, now we know that that is equal to the area that we find in part B. And so if we wanted to represent that other area, we might say that we have 2 minus 0, 2 minus 0 times 5/2. Where did I get 2 minus 0 from? Mm, 2 minus 0 is, yeah, that's exactly, this is the base of the rectangle. This is the height of the rectangle. And together, that would be the purple rectangle that we drew above. Okay. So we've got the area of that rectangle, that purple one. We've got the area of the triangle, the yellow one. And it turns out that we can say area using integral symbols. And then the other half, we don't actually use the integral symbol, okay? Because we're using sort of that idea of base times height. But all of this is to say that we have something called the average value theorem for integrals. And here's what the formula looks like in a typical textbook, okay? A typical textbook will say this. Let's see, how do we want to write this? F of C times B minus A equals the integral from A to B of f of x dx. Okay. So now we've taken away all the numbers. We've got a whole bunch of letters. And let's see if we can figure out how these match up above, okay? So we have this integral notation, just like we have in the green over here. That part is the same. And we'll notice that instead of writing 2 minus 0, I did b minus a, all right? Because if we looked at our bounds, we have b, which is 2, minus a, which is 0. That's where I get that 2 minus 0 from. Okay, so this b minus a is that b minus a. And then instead of calling it the height, I wrote it as f of c. And we know that f of x or f of c, f of any number is going to be a y value. And this y value here in the front actually finds the height of that rectangle. Okay. Now, this is one version of the formula, but more typically, we see it like this. F of C equals 1 over b minus a, the integral from a to b of f of x dx. How did I get from that one version on the left to the version on the right? Like, what happened there? Ah, I love it. I love it. Exactly, right? And sometimes it takes us a minute to think about like what happened, but this b minus a, I literally just divided it to the other side, okay? Now, I think that it can happen that instructors of sort of 151, like that Calc 2 and beyond, sometimes skip some of these steps. And so that's why I'm taking the time right now so that we can start to think about like the idea of like thinking about how someone gets from one step to the other. Okay. And so when we think about how to get rid of this b minus a, all we did was divide it to the other side. Okay. And so if we annotate a couple things here, this f of c is a y value. Okay, in particular, that is the average value. We have the area between a curve and the x-axis. And then this part gives us the average part. Now, again, this idea of annotating a formula like this, not every instructor does that. And so that might be a skill that you're like, oh, I really did help, like annotating it helps me understand the formula. Maybe that's a practice or a strategy that you want to add to your own toolkit. Okay. So now that we have our average value theorem for integrals, let's go ahead and practice it in a scenario where maybe we don't have pictures, but we're thinking about how to actually apply the formula, okay? So I think it's important to think about not just the concept, but also the procedure and making sure those two are really connected. So in this case, we have a function f of x equals x over 2, and we're looking over the interval 0 to 6. So the question says, find the average value of the function over the given interval. And so when we're looking for the average value, what we really mean is we want to find that y value. Okay. We want to find that y value. And so all we're going to do is let's write down that formula so we get a little bit of practice writing it out. And let's go ahead and plug in the things that we know. So what can we plug in? What can we substitute in? Let's think about this. B is 6, A is 0. Excellent. I love it. Oh, so many places I can put that. It's unfortunate that a B kind of looks like a 6. So let's just be really careful when we're writing it out that we know it's a 6 and not a B. X over 2 for f of x. I love it. Okay, so x over 2 and then dx. Now, all of this is good because what I want to find is f of c. Okay. All right, let's clean this up a little bit. We get f of c equals 1 over 6, the integral from 0 to 6 of x over 2 dx. How can we figure out this integral? What are some rules that we've learned on how to handle this? Okay, because I think this kind of function sometimes looks scarier than it is. How do we handle that x over 2, folks?
Take the x out of the fraction, move the 1/2 outside, multiply it with 1 over 6, and then take the antiderivative of x.
Yeah, I think that fraction piece can be so scary. And I love that we've identified that it's really a 1/2 as a constant. Okay, so let's see what that looks like. So f of c equals 1/12. The integral from 0 to 6 of x dx. Looks a lot more manageable now. 1/12. All right. Hopefully by now we know that the integral of x is x squared over 2. We're going to plug in 6 and 0. Okay. And let's go ahead and plug in our bounds. 1/12 6 squared over 2 minus 0 squared over 2. And what do we get? 1 over 12. Let's see, 36 divided by 2 is 18. 18 over 12 is going to give us 3 over 2. Okay. So the new part of this is certainly the idea of applying the formula, identifying what parts we need to plug in and what we can plug in. All right. This part, this computation part, if you are not feeling very confident on being able to move through the computations quickly, then that is a good indicator that you should spend some of your very precious time practicing this idea a lot. Okay, we want to be able to work through integrals just as well as we can work through derivatives. All right. Okay, so part B. Part B says find C such that f of C equals the average value of the function. Okay, and so when we're looking at this particular question, what we're saying is we know now from part A that f of C equals 3/2. Okay, f of C equals 3/2. And now my question is, I want you to find C. So how in the world can I find C if this is all I know? What information might I be able to include here to help out? Mm. 3/2 equals, okay, but how is that going to help us find C? Because I want to find C now. Do you mean this function right up here? Yeah, good call. So f of x is the function. F of c is just that function, but with a c instead of an x, right? So let's rewrite that function. Instead of f of c, I'm going to write c over 2 because the function is x over 2. Okay, so we're just making a substitution here where f of c using the function given is c over 2. Now we have c over 2 equals 3 over 2, which I think we can do in our heads and not get 2, but c equals 3. Okay. All right. So I know that this was on the quiz and it was on the web assign. I think that occasionally, especially as we get into closer and closer to, that next class, it can be very much an expectation of other instructors that you do learning outside of class. Okay. So if you were feeling like, oh, this was kind of a struggle, Again, there are tutoring sessions to sort of patch in those gaps, but part of that math and writing assignment was like, let's find some resources, right? How do we become maybe a little bit more independent in our learning? It doesn't mean that we're not cared for, or that we're not supported, but how can we be just a little bit more independent in that, and realize that, you know, sometimes we need to do a little bit more work, and sometimes we sort of work through an example and then we're able to go from that, okay? Now, I don't want to do this to you all the time, but I think once in a while it is a nice sort of reset to say like, yes, occasionally we will have to learn things independently. And in particular, I know that next week there's going to be 2 shorter sections in the textbook that I'm going to put up a video for. We will not spend time in class covering those, but it is content that you are expected to be able to know and do. And so I just want to sort of start to prepare you for that. There will be a video, there will be notes, but we're going to be spending our time in class doing a lot more sort of practice together. Okay, so the next week there will be an expectation that you are doing a little bit of that independent practice. And then bringing questions as you have them. And by questions, I mean more than I'm stuck. All right. So bringing me like, okay, I think I was able to plug in this part. Is that correct? Okay. Or like, how did you know that the f of x became x over 2? Those are all specific questions. And the more specific you are, the easier it is for your instructor or tutor to help you out. Okay. So that was an aside, but now we have some notes around that average value theorem for integrals, okay? If you have questions on this, I'm happy to clarify any of those at office hours later this week, but hopefully this will be a resource, an additional resource for you, okay? All right, so let's move on to the fundamental theorem of calculus part 1, okay? So this is probably where we really need to dig into our conceptual brain and think about all the things we know about calculus so far, okay? So I just want to sort of give the overarching framework here. We're going to go through example 3, okay? Example 3, and I'll write it right here, is a long way of approaching these problems. Sometimes we will be able to use the long way, and sometimes we will not. And so it's important for us to understand how to work through the long way. But we're going to take a look at a theorem, and then in these 2 examples, we are going to use a shortcut, okay? Now, I would say that the shortcut still involves reasoning. You still have to think about how to apply the shortcut. If you understand how to do the long way, then you will be able to apply the shortcut, okay? No, because there will be, that's a great question. So there's a question in the chat, before I just say no, there's a question in the chat that says, is the long way the safest way to go? I think it is a way to really solidify your understanding, okay? Which is why I don't want to jump straight to the shortcut. However, you are going to get to some complicated functions where you cannot use this long way, okay? So the long way questions on the notes and on the quiz are chosen intentionally because I know we can do them the long way. But the other questions that I'm going to ask us to use shortcuts for, we will not be able to use the long way, okay? Yes, exactly. Now, it is possible that by the time you finish Calc 2, you can come back and look at these problems and be like, oh, now we have more tools to handle this. Okay, but as it stands where we are, this one method, this long wave, will not work all the time. All right, so we really want to make sure we understand the concept and that we can apply it to a shortcut. Okay. All right, so let's take a look at this. Ooh, so many letters and symbols, right? ddx of the integral from negative pi over 2 to x of cosine t dt. All right, let's start with this part. What does this yellow part tell us to do? We've seen these symbols. What do they tell us to do? It's asking for the derivative. Okay, I would agree. ddx means find the derivative. Find the derivative of what? Okay, find the derivative of the integral, right? Find the derivative of the integral. That's what this whole thing is saying. The yellow part is find the derivative of what? The red part, the integral, okay? So let's think about how we work through this. So we are going to find the integral first, right? So we want to figure out what is that integral? Like, what are we going to take the derivative of, all right? And so if I only, haha, look at that. Things I cannot do in a live classroom is just move part of it off the board. But if I only had this question right here, the integral from negative pi over 2 to x of cosine t dt, how would you apply what we know about integrals to simplify this part of the question? Okay, so what do we know about how to rewrite that part that's underlined right now? Good. Okay. So we know that the integral of cosine is sine. All right. So I know that I have sine, but what about these bounds? Because it sure looks like I have a definite integral here. Not quite. That's a really good guess because we just talked about that average value theorem. But maybe let's go all the way back up here. And how do we handle a case like this? Okay, okay. So let me write this down underneath here because I think this is so valuable for in general, but when we find the antiderivative, we plug in our top bound and then we subtract our bottom bound, right? And so if we think back to this part of the question, so not with the 1/6 or the 1/12 in front, but how did we do this part? We did the antiderivative, we plugged in 6, we plugged in 0, and then we subtracted them, okay? So let's come back down to example 3 and do the same thing. So if I only have this part of the question, the function, my antiderivative is now sine t. What am I going to plug in though? I'm going to plug in x and negative pi over 2. Does that make sense? We've seen that little vertical bar notation with the top bound and the bottom bound. And so when we plug in our bounds, we get sine of x minus sine of negative pi over 2. Okay. So let me just pause here for a moment. Sorry for all the zooming back in and out. Stop doing that right now. How are we feeling so far with this first part, like the integral part? Okay. All right. So now what are we going to do? Now we take our derivative. Okay, so we've taken the integral. Now we're going to take our derivative. All right, well, I know that when I take the derivative of a sum or a difference, I just take the derivative of each piece and then I add or subtract them. So I'm going to take the derivative of this, and then I'm going to take the derivative of this, and then I'm going to subtract them. Okay. So derivative of sine is cosine. All right. So ddx of sine gives me cosine x. Okay. Minus. I know that this is very unlike me. I don't actually want you to tell me what value this is right now. Okay. It is important that you know trig values like this, but that's not the purpose of this particular exercise. However, when I take, no, you're absolutely fine. Okay. When I take negative pi over 2 and I plug it into sine x, are there any variables left? No variables. Oh. Okay, so I'm asking you to find the derivative of a number. I mean, a gross looking number, but a number. What is that derivative? 0, yes. Okay. So we've got the derivative of sine became cosine, the derivative of a number, right? Because this is a constant, the derivative of that constant is 0. Okay, well, what are we left with? We took the integral, then we took the derivative, and we ended up with cosine x. Well, hold on just a minute. Cosine x, didn't we see cosine somewhere before? Oh my gosh, Ethan, tell us more about what you mean by that. That is a gem of a statement. Okay, so in the chat, Ethan says it's the same as first dividing and then multiplying by the same number. And to be clear about that, we're not multiplying and dividing. However, if we multiply something by 2 and then we divide by 2, we get back to where we started. Okay. So if, for example, I had x times 2 and then I divided by 2, I would get x. Similarly, if I had x plus 3 and then minus 3, I would get x. Or if I had x squared and then I took the square root, I would get x. So all throughout math, we've had these sort of inverse functions that if we do something to a number, it is so important for us to be able to undo that thing. Okay. And so here, what we've done is we've taken a antiderivative, and then we took the derivative and we got back to the original function. Okay. Now, those of us who are sitting here might be thinking, well, but the one in the original problem had a t and our answer had an x. So how can you say that that's the same? All right. And so if you're sitting here thinking that, that is absolutely valid. I'm wondering if someone can explain to us, where did the t go? Like, why is our final answer in terms of an x and not a t? Ding, 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 A plus, because of the bounds, right? Those bounds that we have there meant that instead of having t as the variable, we actually changed the variable to an x. Okay. So let's make note of these wonderful things that people are saying. So in particular, our final answer should have x, not t. Okay. What else has been said? The derivative of an integral gives the original function. Okay. So one can imagine that if you had in this green here, instead of cosine, you had a very gross looking function that you were like, I don't know how to take the integral of that. That perhaps one thing we might be thinking about is, well, we're just going to have that same function in our answer, except it will be with an x instead of the t letter. Okay. Okay, well, let's, okay. So these are the questions, right? What if the bounds were constants? Or what if they were both variables? Okay. What do you think it would look like if we had, instead of an x up here, that I had another number? Yes, exactly. Exactly. And what would happen is that this would be a number. This would be a number. When you take the derivatives of the numbers, you would get 0 minus 0. You would get 0. Okay. So that's a great point. If the bounds are both constants, then we would end up with the derivative of an integral would be 0. Okay. Okay. We will take a look at what happens when they're both variables, but before we get to introducing both bounds being variables, let's take a look at B here, okay? And I'm wondering, because this is a sort of like a fun skill when we're in elementary school, but is actually a really important skill when we look at any kind of math, is what's the same and what's different. So through our student lens, what is the same and what's different between part A and part B? All right, let's start off with some things that are the same. Pop those into the chat. What are some things that are the same between A and B? We're taking the derivative of an integral. Great. So if I go back to my colors, I can say I have d dx of the integral. Okay, so I have derivative of an integral. That part is the same. All right, I've got t's and I have x's. That part is the same. That's good. That's good. Okay. Someone else, what's different? The bounds are switched. Oh my goodness. Okay, so the bounds being negative pi over 2, that was this part. And then x, which was this part. Okay. But now they're different, right? The x is on the bottom and the negative pi over 2 is on the top. Based on what we know. What do we predict is going to be changed in our new answer? All right, we talked about bounds being switched here last week. Maybe they will be negative. Okay. Okay, so that's our prediction right now, that maybe we're going to go through this whole process, which is the long way. But when we get to the end, we might predict that we have a negative cosine instead of a regular cosine. So let's see. All right, let's go through this the long way one more time. D dx, I'm going to keep my derivative out front. I know the antiderivative of cosine is sine. I'm going to plug in, negative pi over 2. I'm going to plug in x. And so I get the derivative of sine of negative pi over 2 minus sine of x. All right, so there's my derivative. I'm following it all the way through. All right, let's see. Derivative of sine of negative pi over 2. We said that part above was 0. Minus the derivative of sine x is going to be cosine x. 0 minus cosine x gives me negative cosine x. Your prediction was spot on. So we've talked about the bound reversing, meaning we change the sign of our answer, okay? But can someone tell me, using the format of this problem, why this one, the function is the same, but now we have a negative sign? Okay, so where did that negative sign come from if we look at the problem in front of us? And no worries on typing slow, it's okay. All right, but where did that negative sign come from? Okay, because we switched the bounds, that's one way to look at it, but how did it pop out to be negative from like the work that we've shown here. All right. I argue that we could see it also from our steps here that we're going to get a negative. Okay. So yes, we are going to be going right to left, but I argue there's another way in particular we could tell from here that it's going to be negative. Well, we don't necessarily know that negative pi over 2 is smaller because x might be like, you know, negative 2 pi, then it wouldn't be smaller, right? Okay. So one thing to notice here, just like we did above, is in the first example, the constant was the second part. So we ended up subtracting 0. But in this one, the constant is the first term. And so that's where we get this 0 from. But it's also why we end up with that minus sign. Okay, so the minus sign comes all the way from here. It sort of travels through and impacts our answer being a negative cosine x at the end. Okay. Now I'm pointing out all these things because they're going to be important when we look at that shortcut. Okay, so of course, let me say that one more time. Okay, so when we have a constant as the top bound, we end up with a derivative of 0 in the front and then minus the derivative of the function in the second part. And so because we have a 0 minus something, we end up with a negative function as our answer. Okay. So the order of the bounds will change the sign of your answer. All right. I really love how folks are bringing in stuff we learned last week, though. I think that is very valuable. We want to also be able to extend that and maybe see like a different way why that might be negative. Okay. So negative cosine x is how much the area changes per change in t. Yes, you could think about it like that. All right, let's do this last one right here, and then we'll go on break. All right, but this one is the one that Ethan had pointed out earlier, that what happens if we have two bounds that are both variables, right? So now we have an x squared and we have a 2x. Neither of them are constants. Okay. Take a moment. Think about some predictions. What will be similar to part A and part B? And what's going to be different? All right, so let's see if we could put this all on one screen here so you can see that. How do you think the double variable bounds are going to change our answer? All right, so how do you think those double variable bounds will change our answer? Take a moment, send me a message when you have a potential idea. I do have to say that the ideas that people are sending are really good ones overall, right? And a lot of you tend to be shy. You're so nervous about maybe getting the answer wrong that you don't put out an idea, but sometimes you're actually very, very right. So again, the question that you're answering and sending me a message about is, what do you think is going to be different about our answer for part C than our answers from part A and B? All right, let's take maybe another 30 seconds and type in your thoughts. All right, all right. So we've got a few predictions here that there's going to be, in particular, the most common one I'm seeing is there will be two expressions rather than one. Okay, so I'm hearing from pretty much everyone that two expressions rather than one will be our final answer, meaning that we got, sine x became cosine x, and then this one became a 0. But what folks are saying is that that second one will not become a 0. All right, so let's see if that's true or not. So we're going to start by keeping the derivative out front. Let's take our antiderivative, sine t. We're going to plug in x squared and 2x this time. All right, we're going to have sine of x squared minus sine of 2x. And now we want to take the derivative. Okay, so now we want to take the derivative. So if I take the derivative of sine of x squared, what will I end up with? Right. I know we've been doing antiderivatives for a few weeks now, but let's reach back into our brains. How do we take a derivative of sine of x squared? All right. I'm seeing a few folks give me some answers. So we know the derivative of sine is cosine of x squared. And if we just left it like that, We would be so mad at ourselves when we got that assignment back if it was a graded assignment. Why would we be so mad? Chain rule. All right. Chain. We're taking derivatives and that inside function is not x. We better accommodate for that, right? Same thing for the second one, cosine of 2x, but this time I'm just going to multiply by 2. Okay, so this went to here, this went to here. Neither of them went to 0. So for those of you who made that initial prediction, what a great prediction, okay? Now we might sort of rewrite this a little bit. We'd get 2x of cosine of x squared minus 2 cosine of 2x. And that would be as far as I would expect you to simplify. Okay. Now I'm noticing that some folks are getting very creative when they are simplifying things. And I just want to put it out there that excessive simplifying is sometimes a red flag for me when I am grading work, because I know that that is not necessarily the theme of how we simplify a lot of things in this class. However, if you look at resources online that do problems for you, sometimes they simplify way more than we ever would in class. And that is why that is a red flag. Okay, so please make sure that you are thinking about how we simplify in class and making sure that your work reflects that. Okay. But all in all here, predictions spot on. Very, very good prediction. Okay. Thinking of connecting to the idea that when bounds are switched, we get that opposite sign. Thinking that if we know the derivative of a constant is 0 and we have no constants, then there's still going to be 2 expressions at the end of the day. Okay. I know this is sort of only one problem, but it's such a rich question in terms of how many layers of calculus you can show your understanding for, okay? Now, we've been going at this for quite some time now. It seems like a great time for a break. And so I'm going to pause the recording here and stop sharing my screen. All right, so before break, we took a very in-depth look at a long way to find the derivative of the antiderivative. And we made some really important connections that our final answer should have X's and not T's, and that at a more fundamental level, the derivative of an integral will give you some variation of your original function. Now, what that means is we still need to consider whether our answer is going to be positive or negative. Okay, so that's one layer to consider. And the other layer to consider is what happens when our bounds are both functions of X rather than X or a constant, okay? And we made some really good predictions and observations that in that double variable case, we end up with 2 expressions in our answer, but more significantly, we had to recall our good old friend chain rule to help us modify our answer, okay? And so now let's give the actual theorem, okay? So the fundamental theorem of calculus part 1 in mathematical terms says this: if f is a continuous function on a to b, okay? So if f is continuous over a given interval, then 2 things are true, okay? First, the function has a derivative at every point in A or B. And so this capital F of X is like after we take our integral, okay? So the thing that we take the integral of should have a derivative at every point. The second part is really the meat of the theorem, and it says that the derivative of the antiderivative gives the original function, okay? Now this is only going to be true when look at what's at the top bound, just an x, okay? And we have a number down here, okay? So we really want to pay attention to the bounds, and we want to pay attention to the fact that someone is asking us to find the derivative of the antiderivative, okay? So this is only when we're taking the derivative of an antiderivative. All right, so with that, let's take a look at two cases where we are going to need a shortcut because we do not know how to take our integral of a given function, okay? So we're going to start with example 4 over here. And so if we try to do this the way we were doing it before, we would get the derivative of, I don't know what that is, right? I don't know what that antiderivative of 1 over 2 plus e to the t is, okay? But I wonder if we could be clever about our notation and not panic, but say instead, maybe we can use this capital F to say, whatever that function is, we took the antiderivative. And so we might actually write this, F of t, and then we're going to plug in 3x squared, and then we're going to plug in pi. Does that part make sense in the notation? Okay, so we're sort of saying, I don't know what the integral is, but I know that capital F stands for the integral. So I can use that to kind of skirt around the fact that I don't know what it is. Okay. All right, well, how would I, if I knew what the function was, how would I do this next step? Like, what would I do here? What would I write next? Plug in the bounds. All right, so let's do it. Let's plug in those bounds. F of 3x squared minus f of pi. Beautiful. Okay. This is the weird part, right? I don't know what capital F is. But let's think about things we do know. What's going to happen to this? Becomes a 0. Excellent. So this will go to 0 when I take the derivative. Okay. So that means that I'm really thinking about the derivative of the integral of 3x squared plugged into the function. Okay, I'm looking for the derivative of the integral when I plug in 3x squared. What is the function going to be when I take the derivative of the integral? Okay, so what is the function when I take the derivative of the integral? The original function, but with 3x squared plugged in. I would agree. This is where we're using that second part where the derivative of the integral gives us the original function. Okay. And so when we write that out, we'll get 1 over 2 plus e, not to the t, but the 3x squared. Okay. So let's just make sure we've all got where that comes from, that the 1 over 2 plus e to the t, we see that down here, but instead of a t, we have 3x squared. Okay. Now, if we left our answer like this, we would be real mad about it at the end because we would be so close to the perfect answer. What is it that we need to take care of here? What do you mean by simplify the exponent? Can you tell us a little bit more about that? Okay, well, yes, we definitely need to include our chain rule here, this part right here, since this inner function is not just x, we need chain rule. Okay, we need that chain rule piece. And so to get the perfect answer, we would just go ahead and multiply, not by 3x squared, but by that derivative, which will give us 6x. And maybe one simplification, if you wanted, would be 6x over 2 plus e to the 3x squared. Okay. So shortcut in the sense that we didn't actually know what the integral was. This whole time, we didn't even know what that integral was. Instead, we used the idea of the integral to help us find, once we had the idea of the integral, helped us find the derivative of that integral. Okay. So it's a little bit more abstract in the notation because there's no function there, but we're saying we understand that we took an integral. We just don't know what it is, but we know after we take the integral, we're going to plug in our bounds and see what happens. Okay. Now, I know that we know what the integral of sine x is, like in example 5. Okay, but we're going to try and use the same idea of abstract notation using a capital F instead of the actual integral, and think about what that might do to our answer. Okay. Now, before we do this problem, does this look like a question where we will need chain rule or not? Okay, in example 5, does this look like something where we will use the chain rule? Or no, we don't need chain rule. I have a yes. Do we have other thoughts? Yes, no, maybe so. right, we've got a yes and a no. How do we know when we have to use chain rule? Maybe that's the better question. How do we know when we need to use chain rule in these questions? Okay, but where do we see, let's be more specific. Where do we see an inside and an outside function? Like, how can we tell without doing any of this, just by looking at the problem, that we're gonna need chain rule? Okay, can you be a little bit more specific? When X is not by itself, where? Ah, okay. Folks, there it is in the chat right there. How do you know if you have to use chain rule or not? And the answer is exactly as Christina said. If that bound, if that's not just an X, we're going to need chain rule. Okay. If that bound is not just an X, we're going to need chain rule. Check this out. Whoa. X squared, not just an X. We use chain rule. 2X, not just an X. So we use chain rule. Okay. But when we go back to like part A and B, we did not use chain rule because all the bounds were just X or just a number. Okay. So in looking now again at example 5, what do we think? Chain rule, yes or no? Okay. So check out the bounds. Whoops. We've got a square root of X. That is definitely not just an X. As much as we might dislike these square roots, it is not just a function, just X, right? And so we are going to need chain rule here. All right. So I want to make that really explicit because sometimes we just go through problems and we assume we don't need chain rule, but if we can see it earlier in the problem rather than later, then we have a lower chance of making that mistake. Okay. So let's see what this might look like. This is asking us to find f prime of X. Well, f prime is another way of saying find that derivative of my f of t, where I'm plugging in square root of X and I'm plugging in 1. Okay. And so when I keep that derivative on the outside, I'm going to have f of square root of X minus f of 1. That bottom bound is going to be a number. I don't know what it is, but it's going to be a number. So when I take the derivative, it's going to go to 0. And now I'm just left with the derivative of the integral of what would be a better way to write the square root of X? X to the 1/2. Okay. So now we see a little bit more clearly, hey, chain rule, all right? Now, the function that we're going to have in our final answer, what is it going to be? What is the function in our final answer going to be? Yes, it's going to be sine. Very good, very good. All right, so we're gonna get sine as the function because we have the derivative of the antiderivative. All right, and if that's what we left our answer is, we would be so mad because we even labeled it. We need our chain rule. And so we want to make sure we include our chain rule here, which is 1/2 x to the negative 1/2. All right. And I try and do a lot of examples with the square roots because it's still a weak spot in our class overall. All right, people are doing very creative things with fractions. So we really want to make sure that we know it's still the power rule. We bring that power down and we take 1 away from that power. Okay. And so if we wanted to spruce this up a little bit, we might have sine of root x over 2 root x as our answer. Okay. So that, my folks, is the fundamental theorem of calculus part 1. Okay. The shortcut is not necessarily that much shorter, but it does mean that we have to make some decisions and be very aware of why some things have like the chain rule, why some of those are negative and how that happens. But I think if you follow this kind of structure, that you'll find that the reasoning is sort of built into the steps here. Okay. All right, so as promised, that was sort of the meaty part of the lesson. And we're going to spend the rest of the class time talking about the fundamental theorem of calculus part 2, which should look very familiar to us. Yes, that is actually exactly it, Ethan. The most fundamental thing in calculus is you do 2 inverse functions and you get back to the same thing. Exactly. Okay, that idea in math is actually so important that like you have a way to undo the thing that you just did. Because without the ability to undo things, it really limits what we can do with the math. Okay, so it seems so basic, but that's literally all it is. Cool. I do have to say, if that's like the takeaway from here for you, I don't know that I was sort of like mathy enough to, when I was taking calculus for the first or second time, to, really grasp that concept. So know that like the ability to think like this is certainly a skill that can be developed, so if you're not there yet, the more you engage with it, the easier this kind of thinking becomes. Okay. All right, so why would I say that this fundamental theorem of calculus part 2 is actually smooth sailing for us? What does this look like here? The formulas that we see. So read that over. What does this formula look like? It looks a lot like net area. What else does it look like? right? And this is where that vocabulary is really important. Go back to your notes. Even today, there's another name for what we just written right here. You know, kind of like there were a billion ways to say derivative. What is this saying right here? Definite integral. There we go. Net area and definite integrals. Same thing. When someone says, find the net area, they mean do this. When someone says, find the definite integral, they mean do this. Okay, so net area and definite integrals are the same thing as the fundamental theorem of calculus part 2. Okay, same thing. Net area, definite integrals, and this whole formula right here all mean the same thing. All right, so knowing that, let's take a look at this problem. I only included the picture here so that we could kind of predict a little bit what our answer is going to be. But when we look at this, evaluate this definite integral, okay? Or I could say, use the fundamental theorem of calculus to evaluate this, or find the net area between -2 and 2. Those are all different ways I could ask that question. But based off of my diagram here, do we expect our answer to be positive or negative? Right, let's keep on with the predicting piece. Do we predict a positive answer or a negative answer? All right, what are our thoughts? Positive answer, negative answer, how do we know? I've got one vote for a negative. What do we think? Negative, negative. Okay. Well, I buy that. I think if we take a look at what we have here, we've got a region that is all below the x-axis. And so we might predict that at the end, exactly, we're going to get a negative answer. Because this is below the x-axis. Okay, negative answer because it's below the x-axis. All right, so let's get started. The integral from -2 to 2 of t squared minus 4 dt. What's our first step in evaluating that, folks? What do we want to do first? Find that antiderivative. All right. So antiderivative of t squared, what do we get for that first term? T squared, what does that become when I take the antiderivative? 1/3 t cubed. All right. I'm going to do t cubed over 3. Some instructors really like to write it as one fraction. Some really like to write it as 1/3 in the front. Okay, but they mean the same thing. And so being flexible between those two is a good idea. Now, what happens to the 4? When I take the antiderivative of 4, what do we get? All right, we want to make sure we have the proper variables here. So I like the idea of 4x, but let's make sure it's a 4t. All right. All right, there we go. Antiderivatives done. Now I got to write my bounds, 2 and -2. Okay. What do I do next? Plug in the 2 and then plug in -2 and subtract. There we go. So 2 cubed over 3 minus 4 times 2. That's the top bound minus -2 cubed over 3 minus 4 times -2. All right, there is our fundamental theorem of calculus part 2. There is our definite integral. That is our net area. Okay, all that same process. All right. If I can give you one word of advice here, it is this: be very, very careful with your signs. Okay, one wrong sign could mean that you end up with an entirely different answer. Okay. I do also want to be clear that the expectation here is that we are doing these by hand and not by calculator. All right. So when the numbers are sort of small like this, we want to be able to do these by hand. All right. So let's make sure that we've got our number accuracy hat on. What do we get when we take 2 cubed? Eight. All right. So I have 8 over 3 minus 4 times 2 gives me 8 minus, all right. What happens to the -2 cubed? What does that give us? -8, I love it. -8/3. And then what about that last term here? -4 times -2 is going to give us a +8. Good, good, good. Okay. All right. Now, let's go ahead and collect terms that have like the same denominators. Okay. Now, I'm being really explicit about this, not because you need it for this particular problem, but as a general problem solving strategy, I think this is helpful. So what I'm going to do is I'm going to collect my terms that have the third on the bottom. All right, so I'm going to collect those together, and then separately, I'm going to collect the terms that have just a whole number. So I get 8/3 plus 8/3. Why is that a plus? Two negatives make a positive, beautiful. And then I'm going to get -8 and then -8. Why is it a -8 at the end? Negative and positive make a negative, exactly. Okay, so this is exactly where I see mistakes being made, is that we might not distribute appropriately, and then a lot of things end up canceling out, okay? But now that we have grouped them by like terms, we can do 16 over 3 minus 16, and I might even put that over 1. So I want to find a common denominator. So I'm going to get 16 over 3 minus, let's see, 16 times 3 is 48, I think. Yes, no, someone double check me on that. Yes, 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 thank you. All right, and final step, we end up subtracting, and so we will get negative 32 over 3. And as predicted, we get a negative area, and that's okay because our picture shows that all that area is underneath the x-axis. Okay. So questions about this? Very mechanical process. Just got to be really thoughtful about our numbers here, that they have the proper signs, that we're computing numbers accurately. Okay. Now, I want to take a moment and show us a different way to approach this problem that I think will be something that we use a lot in the next unit. And it is more about being clever in our setup so that we don't have to worry about quite so many fractions. Okay, so if you were like, I don't like fractions so much, I would rather have an easier computation to deal with, and this next method, so long as it fits with the picture, is a good method to have. Okay, so let's go back to the original picture. I highlighted this whole yellow area. Okay, you have to know that it is exactly a specific shape. Okay, so the problem has to tell you this is a trapezoid, or this is a circle, or this is a triangle, in order for you to use the area formulas. All right, yes, exactly. So we want to make sure that we're really thoughtful, not just that it kind of looks like a semicircle, but that we know for a fact it is. Okay. All right, so let's go back to this. Let me get rid of that yellow area. And now observe this. We know that parabolas are symmetric, right? And so, oops, it might, in fact, be interesting to think about this purple part. All right, that purple part. This purple part has the same area as the blue part. Okay, so the purple and the blue, same area, right? So instead of setting up my integral from -2 to 2, because this is symmetric, okay, so only for symmetric regions, here's what we can do. We can say, instead of finding the area from -2 to 2, I'm going to find the area from 0 to 2 of t squared minus 4 dt. And if I have only that integral, that gives me the purple area there. Okay. What is a clever way that I can use this answer to get the whole answer? Multiply it by 2. That is exactly it. I'm going to put a big old 2 in front of here. This 2 is exactly what Megan said. This 2 will double the area of the purple area. And then that will give me the area of the entire region. Okay, but you can only use this if you know 1/2 is the same as the other half. Okay. So let's see how this changes our problem. We're still going to, I think as Isaac said, we're still going to take the antiderivative. So, or maybe it was Eric. So we'll get t cubed over 3 minus 4t, but this time my bounds are 2 and 0. Okay, now keep the 2 in the front. We're going to plug in 2. And then we're going to plug in 0. And then check out what happens. 2, 8/3 minus 8. Oh, we still had to do that, but what happens to this entire second piece? This whole second piece goes to 0. Oh, okay. So what that means is we have 2 times 8/3 minus 8/1, which is 2 times 8/3 minus 24/3, which is 2 times -16/3, which is -32/3. So in this context, I think the fractions were not that bad. 8/3 and 8/3, we can add those. 8 and 8, we can add those. But in some of the other problems we'll see, it's actually going to be significantly less work if we can use symmetry and then just find half the area and double it. And the best time to use half the area and then double it is when you can make that bottom bound 0, because it makes this part so much easier to calculate. Okay. You don't have to use that right now, but it is something we will use a lot in the last unit. Okay, the idea of symmetry, because we're going to take all these integrals and they're going to get even more gross. And so we want to sort of save ourselves as much work as we can. Okay, so you can grind through it, do it sort of the longer way, or if you're ready to start to think about how to be more clever, look for symmetry. Okay, but know that you can only use this if you have symmetry. All right. Yes, exactly, exactly. So this in particular is an even function. So if you have an even function, cut it in half, double it. But if you have an odd function and one of those is positive and the other one's negative, you'll end up with an area of 0. Okay. All right, let's see. I do want to do this question here. I think this will be a good place to stop for today, and we'll do the last example when we come back on Wednesday. But this one, okay, looks kind of gross, right? We've got a fraction, how dare they, on a Monday morning, and we've got a square root. Now, what are some ideas we might have around handling such a problem? This is going to require you to think way back to like before we learned all of those derivative rules. And there were some things that we were able to do to make our lives a little bit easier and to make questions a little bit more accessible. What could we do to solve a question like number 10? Conjugates, okay. Now I notice the conjugates are typically with the square root. In this case, it's just square root of x. So the conjugate of that is just square root of x. So what would that look like? If I did conjugates, it'd be like x minus 1 square root of x times square root of x over x. And that would give me x minus 1 times the square root of x over x. So conjugates is a mathematical strategy, but I'm not sure that it makes it better in this case. Okay. But it's good that we tried it. Okay, well, yeah, exactly, right? And so here's the thing. The folks who are teaching your classes have probably done this so many times that they'll be like, of course you shouldn't do that. But how are you going to know, right? So it's useful to sit and write it out and be like, did that make it better? No? Okay, then I'm going to stop. Okay. Okay. So I see 2 who are saying, let's do something with this square root of x. So maybe an alternative is that we could say we have x minus 1 times x to the negative 1/2. All right. And let's see if this helps. Does it help that we took the radical in the bottom and used the ideas of exponents to rewrite it so that now we have a product instead of a quotient? That's not a bad strategy. What would we do from here? Yes, this is a sideways parabola, but algebraically, what can we do from here? Distribute. Okay, why not? We tend to distribute when we see things with parentheses. And so if we distribute, what do we get? Right, and so I do want us to think about what we get when we distribute, because all these exponential rules come in so handy. All right, so we get x to the 1/2 minus x to the negative 1/2. Okay, I agree with that. And if you're not sure how we got from this step to that step, really encourage you to go back and brush up on your exponential skills. Like, how do you combine exponents? All right, that is such a valuable skill. So go back. I'm sure Khan Academy has a bunch of videos on those exponents. Gotta know them. Okay. Now, can we take our antiderivatives now? Like, did this make it better? Is really my question, because we tried one thing and it did not make it better. So we tried a different strategy. Did this different strategy make it better? Yeah, I would agree. I would say yes. It made it better because even though there are fractions and negatives, it left us with the power rule, and we know how to use the power rule. Okay. So let's do it. I'm going to write it out so that we know where all the numbers come from. Because again, I've been seeing a lot of very magical, and not necessarily in a good way, magical things happening with fractions, and people are panicking, and it's almost like you would rather not take the time to write it out than you know, actually just guess. So we really want to make sure we understand where this comes from, okay? So we're going to do x to the 1/2 plus 1 all over 1/2 plus 1. That is the integral of the first part. Minus, what's different about the next one? Negative 1/2 plus 1 over negative 1/2 plus 1. I'm going to plug in 9. I'm going to plug in 1. Okay, but we're going to simplify a lot before we get there. X to the, what does this new power become? I know these are boring kind of questions, but I want us to make sure we're getting our computation in there. 3/2, great. What's in the denominator? Three halves, good. Minus x to what power in the second term? What do we got over here, folks? X to the negative 1/2 exactly goes to 1/2. And what about the denominator? What do we got for the denominator here, folks? Last denominator. 1/2, good. All right, we're gonna do one more thing before we plug in our numbers. If I have 3/2 on the bottom, it is the same as having 2/3. Okay. How do I write x to the 3/2 as a radical? Okay, how do I write it as a radical? Square root of x cubed, excellent. So square root of x cubed, good. Minus, if this 3/2 in the bottom became a regular 2/3, what does this 1/2 on the bottom become? A 2, perfect. So minus 2 and x to the 1/2 is just the square root of x. Now let's plug in our numbers. 2/3, the square root of 9 cubed minus 2 square root of 9 minus 2/3 square root of 1 cubed minus 2 square root of 1. Okay. All right. 2/3. 9 cubed is 9 times 9 times 9. Minus this becomes 6 minus 2/3 plus 2. How can I simplify this without a calculator? All right, how do I simplify square root of 9 times 9 times 9 without a calculator? Not quite. I bet you know what this is. Square root of 9 is. What's the square root of 9? 3. Okay, what's the square root of this 9? 3. What's the square root of this 9? 3. They're all 3, okay? So we really have 2/3 times 3 times 3 times 3. All right. So we can apply that square root to each individual part as long as they are multiplied. I know y'all are overcomplicating things. Okay, which is 27, but let's be clever about this again. 3 and 3, those cancel out. So we actually have 2 times 3 times 3, which is 18 minus 6 minus 2/3 plus 2. Let's combine all our, yeah, I know you guys were, okay? And that is precisely like when you might encounter professors that are like, don't use a calculator, which I know we're online right now, nobody can control that, right? But thinking about like why these questions are non-calculator questions, because we can just take it piece by piece and do that first. Just like I'm dividing the 3 away so I can multiply smaller numbers here, okay? All right, so 18 minus 6 is 12, plus 2 is 14, minus 2/3, and that is going to give me 13 1/3, or I can say this is 40/3. Okay. So this works out that we got a positive answer because our picture is all above the x-axis, okay? Now, that's a really good question here. This idea of splitting these up like that is only true when they're all multiplied or all divided. As soon as we introduce pluses and minuses into there, that rule is totally off the table, okay? So you'll get a lot of chance to practice computations in this week's quiz. There's a lot more computation on this quiz than there have been on past quizzes. So I would encourage you to take this as an opportunity to think about how to do these things. All right, especially if you feel like, yeah, algebra is not my strong suit and you are planning to continue on to Calc 2. This right here, yes, I know you could do it in a calculator, but the idea of the computations, you're probably building a very strong foundation for Calc 2 right there. Okay. So it's not all for nothing. It's a great opportunity to build that fluency. Okay. So as I said, this will be the last question we do. When we come back on Wednesday, we'll take a look at this application question, and then we'll be doing a bunch of examples on Wednesday. There's not a ton of new content. It's mostly a lot of examples. Okay. So I'm going to stop sharing my screen here.